This is the 7th lecture in this course, and so the idea for this, the topic for this course is to understand what is called division algorithm. Division algorithm for multivariate polynomials. So let's look at what we know. So one variable. Suppose R is kx. So again, k throughout these things, k is a field. Kx. And let's say f and g are R and g is non-zero. So then, what does the division algorithm say? There exist q and r inside R such that f is q times g plus r, where R is 0 or the degree of R is less than the degree of G. So this is the most basic version that we know. We just divide f by G and then prove that this is true. But how do we see this? Because we would like to generalize such a statement to larger number of variables and possibly larger number of G's also. But how do we see this in this new language of term orders? So note that, monomial orders, note that there's a unique monomial order on R, which is so 1, which is less than x squared, less than x, and so on. We already notice that if x divides one monomial divides another monomial, the smaller one is lower in the order. So there's only one order this way. And then what we are saying is that the initial term, so then R equals 0 or degree of R is less than degree of G. So this is the condition on R. Is the same as R equals 0 or the initial term of G does not divide any term of R. But really, we are just reinterpreting that in terms of initial terms, leading terms. Okay? That's because the degree this is less than this, the initial term is x to this degree, while all of these things here have smaller degree. All the terms here have smaller degree. So this is the statement for one variable. This has been, we have already used one version of it in multivariables, where we have one new variable and a morning polynomial. So that's not exactly the generalization that we want or we're looking for. So here's a theorem that we will prove now. Let R be a polynomial ring in some finitely many variables. F and G1 through Gm inside R. We want to divide F by these. The whole family, not just by a single. Then there exists A1 through AM inside R such that AM through AM inside R and R inside R such that F is AIGI plus R. Okay. Now again, what is the condition on R it's exactly as the one that we stated earlier, where R is 0, or R is such that no term of R is divisible by the initial term of GI. So again, there is some underlying monomial order. Okay, on GI for any I. Okay, so this is the division algorithm or division theorem for multivariate polynomials. So this is always with respect to a given monomial order. The basic case was also with respect to a given monomial order. It was just that it was implicit and we never thought of it as a monomial order. But the principle is the same. Okay. So how do we prove this? So proof is a little algorithmic, and so it's a little informal maybe. So I'll try to explain the algorithm, and then we will see an example in my colleague too, where we work through the algorithm, and hopefully that you would understand. So if you look at the book of Cox, Little and O'Shea, then there is a formal way of where the algorithm is written and its termination and correctness proved. So we will do it somewhat informal. Okay, let's do the following. Okay. So we ask so proof. Proof is, we will construct some elements and then we will prove that this is enough. Okay. So proof of the theorem. So at every stage we ask the following question. So this is the starting stage. If there exists J such that initial term of Gj divides the initial term of F, then okay, we just remove the initial term. F1 we define to be F minus, so a suitable coefficient here. So I'll just write a box here because this to be suitable coefficient. The idea is that we want to cancel the leading term. So we might have to use a coefficient depending on what the coefficients here are. In F divided by in Gj. So I might forget to write the symbol for the order, but there's only one order, so in refers to in with respect to that, times Gj. Okay. So again, we repeat, this suitable coefficient here is put in so that the leading term coefficients are cancelled and the leading term is removed from this. Okay. So this is what we do. Okay. Otherwise, okay, just take F1, define F1 to be F minus the leading term. Okay. There's no J to be adjusted. Okay. So this is the step that we will do at every stage, and we would need, when we come back after later, we would need to keep track of what was the step that at every stage is. So we will write for this one, we will write C1 equals 0. In this proof, we just have to keep track what was the operation that was done at every stage. Was it cancelling the leading coefficient by suitably multiplying a Gj, or was it just subtracting the leading term? So this has to be kept track when we come back to finish the proof. So we will denote this thing, that we cancel the leading term by a suitable Gj. That statement we will keep track by writing C1 equals 0. And this one we will denote by saying C1 equals 1. So this is, I mean, there is no significance for the numeric value 0 or 1, which is just a binary value. One has to just keep track of what did we do to go from f to f1. So this. Okay. So now let's observe this thing. If f1 is non-zero, then what we just did was to remove the leading term, and therefore in f1 is less than in f. In either one of those steps, the f1's leading term is strictly smaller than the leading term of f. Okay. So now repeat this. Okay. Just continue constructing this. Okay. So then we ask the same question. We ask the same question. If there is a j such that in gj divides in f1, then modify, get an f2 with this property or an f2 with this property, keeping track of what c2 would be. Okay. So let me just write it once. Define f2 to be f1 minus some suitable coefficient here times in f1 divided by in gj times gj. Okay. If there exists gj such that in gj divides in f1. Okay. And here, if otherwise we will just write f1 minus in f1. Okay. And as earlier, we write for this one, we write c2 equals 0. C2, here we said c1 equals 0. This is the modification. And the modification is just blindly removing the leading term. Then just call it c1. C2 equals 1. Okay. So repeat this, and then we ask if f2 is non-zero and so on. Okay. So if f2 is non-zero, the initial term of f2 is less than the initial term of f1. Okay. So now we saw this proof earlier. This cannot go on forever. Okay. So this cannot go forever. Because otherwise we would get no infinite descending chain of monomials. This we proved in the course of proving Hilbert basis theorem. We made this observation. Okay. So this cannot go on forever. So now what does that mean? It means that at some stage fk is 0. So this now implies that there exists a k such that fk is 0. Okay. So now we ask, what is fk minus 1? So of course, to go from fk minus 1 to fk, we would have had to make a choice, which is like this. If it's divisible by a gj, this is the change that we would have done. If it is divisible by, if it's not divisible by in gj for any, this is the change that we would have done. And this data is kept track in, for fk, it would be, for constructing fk, this data would be kept track in ck. So let's use that information. Okay. So two possibilities. If ck is 0, so in other words, if ck is 0, so let's look at it this way. Ck is 0 means this is the change that we would have done. And in other words, fk minus 1 is a multiple of gj. Okay. Fk minus 1 is a multiple of gj for some j. Okay. Ck is 1. So let's just go back here. Ck is 1 would mean that fk was obtained by just removing the leading term of fk minus 1. In other words, fk minus 1 is a monomial not divisible by in Gj for any j. So this is how we would write. Okay. So now the point is, each time we see a term like this, we will keep it with the remainder. Each time we see a term like this, we will add that to the sum of ai gi. Okay. So that's the idea. Okay. So now let's write this thing properly. Okay. So how do we write? Okay. So this is just description. So in the language of the theorem, we would write if ck is 0. So notice ck is 0 means this is a multiple of that. So it would be, so we would write f k minus 1 is some 0 times g1 plus some some aj times gj. Okay. Maybe we will just put an index here to say k minus 1, to say that we are worried about in the k minus 1 stage, and so on up to, so this is an element of 0 times gn, okay, plus 0. This is the stand-in for the remainder, the r. Okay. If ck is 1, then we would just write fk minus 1 is 0 times g1 plus 0 times gm. None of the g's are involved, plus fk minus 1. Okay, so notice that this is what r is, and in this case this is what r. So we are just going to write fk in the fashion what the theorem wants. Okay, so the theorem holds for fk minus 1. Okay, let's just do one more step, and then we will work out. Then we will work out an example. Okay. Let's ask about fk minus 2. Okay. So now what we have to ask is, so if ck minus 1 is 0, so then fk minus 2, let's go back. How would we have constructed fk minus 2? We would have constructed like this. Fk minus 2 is fk minus 1 is fk minus 2 minus some multiple of gj. This is if c is ck minus 2 0, and so on here with this term. Okay. So ck 0, it says that we are trying to find fk minus 2. So not fk minus 2. Okay. So we would have written fk minus 1 as fk minus 2 as fk minus 1 plus a suitable multiple of, so this box here says element of r. Times gj for some j. Okay. And if ck minus 1 is 1, then fk minus 2 is fk minus 1 would have been obtained by fk minus 2 minus its initial term. So it would be fk minus 1 plus an initial term that is not divisible by, so by plus a monomial not divisible by by in Gj for any j. Okay. So now we can go back to this sort of a construction. Fk has this property. So now if ck minus 1 is also 0, then fk minus 1 plus a multiple, so then a coefficient here would have got changed. If this is the if ck minus 1 is 1, then this part would have changed. So in other words, depending on the value of ck minus 1, either the coefficients of Gj in this half of the expression would have changed, or the remainder would have changed. But so that's the okay. So repeating this, we get the theorem. Okay, so that's it. So now I would just like to illustrate this proof using a correct example. So here R is a polynomial in two variables. Monomial order is lex, and f is x squared by xy squared and y squared. G1 is xy times minus 1, and G2 is y squared minus 1. Now, so we are going to sort of go through that algorithm. F1's leading term is x squared y. G1's leading term is xy. So we multiply by x, subtract. So this is the situation where C1 is now 0. This is how we modify it. So we get a new polynomial. This one's leading term is xy squared. That's again divisible by this leading term. So by multiplying by y. So we modify to get f2 to mean this. Okay. So this is again the C2 is also 0. So this is the modification that we do. Okay. So now we get x plus y squared plus y. Its leading term is x. This is lex, so this is the leading term. It is not divisible by the leading terms of any of the g's. So we just remove that leading term and define it. So we write f3 as f2 minus x. And this is a case where the change ck is 1. Okay. So in the previous two stages it was 0, now it is 1. So we just forcibly remove the initial term. So we get y squared, whose leading term is divisible by this leading term. So yeah. So then we subtracted the f3 and g2 are the same leading term, same coefficients also. So we subtracted and we get y plus 1. So this is an expression in which no term is divisible by any of the leading terms. I mean, if you do two more steps, we would get 0. And now we can work backwards. F4 is of the form no term is divisible by any of the initial terms. So that is put in the remainder part. Okay. Now let's go back. Here the change was 1. In other words, we had forcibly removed a leading term. So put that in the remainder. So we got x, this y plus 1 and the x from the previous step. So now we are in this stage where there's a multiplication by, one more stage. Yeah, there is a multiplication by y, y times g2, g1 and x times g1. Going from this to the previous stage is subtracting a multiple of g2. That's because so that would be added in this part. So minus g2 here would be plus g2, and then y plus 1 was this. In the previous step, we had forcibly removed an initial term x, so that goes to the remainder term. And then we do two more steps, you get an y times g1 and an x times g1. A y times g1 from here and an x times g1 from there. And that is that is how the algorithm works. And this is exactly how the proof of the theorem was. Okay? So this is the end of this lecture. And in the next lecture, we will introduce this notion called Grosvenor basis and use them, see some basic examples of